And come from Stony Brook University, and today I'm happy to present our work with the title Scalable Equivalence Checking and Verification of Shallow Circuits. And this is my joint work with Nengkun from Stony Brook and Thomas from University of Wisconsin. And before we go into the concrete problems, I would like to start with some news. Recently, a scientist working on quantum hardware was awarded the Nobel Prize in Physics. This recognition highlights the growth of global attention and investment in quantum technologies, both from academia and industry. It reminds us that quantum computing is no longer a theoretical but an engineering and verification challenge that we need to solve today. Let's see the motivation of our work. Equivalent checking of quantum circuit is a fundamental verification task. And to translate our computation model to a quantum circuit that can run on a real hardware, we need compilers. So equivalent checking ensures that compiler optimization preserves the correctness of the programs. And why should we take care about shallow circuits? Shallow circuits are the class of circuits with constant depth, and they are particularly important in the near-term era because of some reasons. First, they require only short coherence time, which makes them suitable for near-term hardware. And remarkably, they already demonstrated quantum supremacy in Google's experiments in 2019, meaning that they can outperform classical machines in certain tasks. And a simple example of a shallow circuit with 8 qubits at depth 3 is here. Each layer applies 2 qubit gates on a pair of qubits with time progress from left to right. The gates are unitary operations, and quantum state of the system is represented by a vector. This gives us a concrete structure in 1D to keep in mind, but we can also consider circuits with more complicated structure in 2D, 3D, etc. And the most direct way to check equivalence between two circuits is to simulate them classically and compare the outputs. Given a circuit C and an input state psi in, we apply the circuit to get the input, the output. Sorry. And there are two simulation types. The first one, strong simulation, where we compute the exact output probability for every output string. In weak simulation, we sample bit string from the output distribution to mimic the behavior of quantum devices. Unfortunately, both methods require exponential resources in number of qubits. And so while simulation is intuitive, it does not scale. Additionally, some worse news come from complexity theory. DiVincenzo showed that if shallow circuit can be simulated efficiently, then the complexity class BQP is a subset of the class AM, a classical class. And then it means no quantum advantage against classical machines. Then after that, G and Wu proved that approximate equivalent checking for shallow circuit is QMA hard. We remark that BQP and QMA are the analogs of the class P and NP in classical complexity. Then these results suggest that simulation is unlikely to be the path to efficient verifications. And up to this point, it's still unclear whether efficient equivalent checking is doable. And in fact, conventional wisdom would say no. First, equivalent checking is another form of verification. And most verification methods rely on exploring the state space to check some key properties of the output. But exploring the state space of a quantum circuit somehow means simulating its behavior. So if equivalent checking were easy, then simulation should be also easy, but it's not. And surprisingly, we discover a method which is scalable and classical, which avoid exponential simulation entirely, and we call it projection-based representations. Here's a quick preview of our results. This plot compares the runtime of equivalence checking for circuit update 3 using traditional state vector simulation versus our method. The red and green curves show the runtime of the state vector simulation method. They exponentially blow up when the number of qubits increases. However, the orange and blue curves show our method's runtime that scale linearly with the number of qubits. And this computational advantage allows us to scale verification to larger circuits. And let's formalize the problems. We consider two variants. The first one, fixed input equivalence. The question here is whether two circuits produce the same output on the on-zero input state. And the more general versions, arbitrary input equivalence checking with the questions whether two circuits produce the same output for every input state. And we restrict ourselves to consider constant depth circuits with arbitrary gate set, and each gate only acts on a constant number of qubits. Let's see our key idea. Instead of storing the output state as a vector explicitly, we represent it using a tuple of local projector, projection matrices, P1, P2 to Pm, and each projector acts on a small set of local qubits, which is determined by forward light cones, a concept that we will revisit very soon. Then the output psi r will be the unique common eigenvectors of these projection matrices. Okay, here's an example for the forward light cone of qubit Q3 and Q4 in the qubit in the circuit that we see earlier. The gates in the light cone are blue, and the side of the light cone is bound by the constant depth and independent of the number of qubits. Local position will be computed inside this light cone, and the number of light cones is linear in the number of qubits. Let's see how it works. Our algorithms begins by initializing local position. For example, here for qubit Q3 and Q4, we start from projector corresponding to vector 0, 0. Then we update the projector layer by layer using Heisenberg picture for evolution of quantum operator, where U is the unitary operator acting on the projector support. Finally, the intersection of these local position images fully characterize the output state. We apply that representation to check equivalence between two circuits C1 and C2 for fixed input or 0. The problem will be reduced to checking whether the circuit C1 dagger C2 performs an identity operation on the on-zero state. And we know that C1 dagger is the inverse of C1 because it is a unitary operation. And we compute the local position of this combined circuit and check if the on-zero vector is in the conjunction of the images. In summary, we transform equivalence checking into checking a set of local constraints. And for arbitrary input equivalence checking, we apply choice isomorphism to reduce the problem to a fixed input equivalence checking with a larger circuit. And the processes avoid full state simulation entirely. We also analyze the complexity of the method. The runtime T and D is linear, in the number of qubit n for fixed depth, and the exponential blow-up only depends on the depth d of the circuit and the geometry of the circuit. And here we show runtime for computing local position for random circuit in 1D at depth 6 with the blue curves. The red curves present the runtime for state vector simulation, which quickly becomes infeasible. And in contrast, our method scale linearly and run comfortably up to 200 qubits on our device. We compare our equivalence checking with classical state vector simulation method on the same machine. And on the left is the runtime for checking depth 3 circuit. We already seen it earlier. On the right is the result for depth 4 equivalence checking. State vector simulation seems faster at small size circuit, but this is only because we stop it early. Each runtime will explode right after that, or in some case, or in many cases, the memory will be insufficient to run simulation. And this highlights the clear advantage of our approach for larger system. Yeah, and this is the scaling for runtime in the problem of arbitrary input equivalence checking. It is still linear in number of qubits. Before the conclusions, we highlight the two applications of our method. The first one is an efficient classical description for shallow quantum circuit output. Then in the paper, we also design a class of assertion languages to verify compiler translation and operation on quantum devices. Then let's wrap up. Shallow circuits are important, but traditionally hard to verify. And we introduce a projection-based method for exact equivalence checking that scale linearly in number of qubits at fixed depth. And this enable practical verification and runtime assertion checking on real devices. Yeah, thank you for listening, and I'm open for your questions. Thanks.
We have time for questions. Yeah, please walk up to the mic if you want to ask.
Very nice. I have a question. So already for depth 4, things become much harder.
Yeah.
I want to know how many gates do you have in there when you have n qubits and say depth 4. How many gates are we talking about in the circuit at that point?
Yeah. Let me.
So in particular, can you do up to like close to 4 to the n or 2 to the n?
Yeah. The circuit that we run these experiments on, they are of the same structure here, with the same structure and up to 200 qubits for each circuit at depth 4, and each gate random unitary matrices. Yes.
So one question I had is, it seems like the method that you presented works very well at 3, and at 4 state vector performs very well. I mean, at least for the experiment that you had shown, right?
Yeah.
There's an explosion. Is there, is there opportunity for thinking about a combination of these that might work for better depths? I'm curious why, when you mentioned shallow, it was like 3 and 4 seem like both seem shallow.
Yes. 3 and 4, in fact, we have a method to classically simulate quantum circuit efficiently in depth 1 and depth 2 already. And depth 3, we just present just very first experiments in depth 4 and depth 3, just they are still very first result, and we will continue the works.
Excellent. Yeah, thank you.
Thank you.
Let's thank the speaker again.
Thank you.